Sure, yeah. So this is the second workshop. Um, so in this workshop, we're going to be introducing you to some of the fundamentals of machine learning, and it also over the course of it, just essentially talking through. At the end of the day, it just boils down to a lot of problem solving steps, and that entails understanding the problem, understanding what approaches could potentially help, and then how to evaluate a problem. So with that said, I think I'll turn it over to Ramita to start sharing some of our Google Colab notebook. So that's the other thing here is along the way, we're also going to hopefully get you introduced a little bit to coding in Python. We're going to provide you with some code that, even if you don't have, a background in programming specifically or a background with, Python in particular, we'll provide some examples that will kind of get you up to speed and introduce it to you.
Okay, thank you, Dylan. Thank you for the introduction. So, hey everyone, welcome to workshop day 2. So, as Dylan mentioned, we will be mostly talking about very basic fundamentals of machine learning today. And we will also walk you through some basic examples just to have a basic idea how it works with machine learning. So, a couple of points before I start. Please feel free to interrupt at any point of time if you feel you need more context, you need more explanation, or you cannot understand something. Please feel free to interrupt and speak up. And like even if you can also type things in the chat box, and I will ask other mentors to help me out with the chat because I think I won't be able to access the chat when I'll be doing screen sharing. So, okay, I think we can start now. Let me share my screen. I believe the screen is visible to you.
It is.
Okay. Okay, so let's get started with day 2. So to start with, we majorly 3 takeaway points from today's workshop. So we will start with understanding what is the problem, and then we will go to whether machine learning can help us to solve that problem. And once we figure out whether machine learning can help us or not, we basically will understand how to solve that problem. So to answer the first question, I think most of you kind of have some sort of idea of how to deal with the first part of the problem, because in workshop 1, we kind of learned about some sort of audio, video, and image processing stuffs. So what the first problem essentially tells us to understand is what is the input and what is the output. So to say in simpler words, so if we are considering a problem of from an image, we are asked to say whether the image is of a cat or a dog. So in this case, we know the input is an image and the output are the labels of whether it's a cat or a dog. So the basic step is to understand what is the input and what is the output. Once we have a clearer idea of what is the problem, we can actually try to understand whether machine learning can help us in solving the problem or not. So we will go in more detail in cases where we don't really require help of machine learning, but it's important to understand when and when not to use machine learning. So once we are sure whether machine learning can help us or not, then we can jump and see what are the different ways in which machine learning can help us to solve the problem. And even if once we have kind of a solution, it's important to know how well the solution is helping us out, like to what extent it is actually solving the problem. So these things are majorly discussed in the answer to the third question. So to start with, I will just do a quick recap of what we did in workshop one. So in workshop one, we majorly talked about three parts: processing images, processing video, and processing audio. So we started with images. We knew we came to know what is histogram, what is like some image thresholding, what is filtering, augmentation, and those stuffs. Next, we moved on to video processing. We came to know about different formats of video, conversion between different video formats, and then also we played around with the changing of the speed of the video a little bit. Next, we did some basic stuffs with audio processing as well. We came to know about different representations and some augmentations with audio as well. So today, based on what we learned, we will start with feature engineering. Now, we kind of had a little bit of idea of how to deal with features, but in the workshop one, we didn't really know we were dealing with features. So for solving any problem, there is a best way to not every representation of data is very suitable for solving the problem. So we need to know what is the best possible representation to solve a problem. Features actually did that job. Features actually do that job. So it's extremely important for us to know what is the best possible representation to feed a system to reach a solution. So feature engineering essentially does that job. So for every problem, we have to first know what are the features. Once we know what are the possible features, we have to do the extraction of the features. Once we do the feature extractions, again, not every feature is very essential or very necessary for every sort of problem. Then we need to do feature selection. And once we are done with these three steps and we are very sure about the quality of the features, then we can actually see how the model is or how the system is working with those features. So to start with, since kind of we kind of have an initial or elementary idea of what are features. So let's just quickly jump to a very basic problem. Suppose we are given this we are given the table that we can see on screen right now. So we need to differentiate between two set of plants, like the small leaf plants and the big leaf plants. And we have the two different set of data, like we know what are the width of the leaves and we know what are the lengths of the leaf. So the first question comes, what are the features in this case? It's a very elementary example. I think it should be like pretty easy for you people. So please feel free to speak up or in chat. Uh,
All right, so we have Chris in chat who says that the features are the width and the length.
Okay, good job. So yes, that's the correct answer. So here, the width and the length are the features. So as we can understand that features are nothing but the basic measurements or descriptions. So here, like the width and the length is actually helping us to answer the question, which species is the plant. So again, it's nothing but the best possible representation that can help us to solve a problem. So now moving on to the fact like what feature extraction actually look like. So here we for the first example, we kind of have very easy features. We knew like only the length and the width are the features, but not every time it's that easy to transform the raw data from like a representation, which can be easier for the system to deal with. So this transformation to from raw data to the feature vector is what we call feature engineering. So uh, so that is, I mean, there are different basically methodologies to convert from raw data to feature vector. I'm not going into the details, but if someone is interested, there are links in the collab that you can refer to later. So So let's think of any any feature that we actually learned from workshop one, because in workshop one we actually dealt with many audio, video, and image processing techniques. So can we think of anything from workshop one that is essentially a feature? Can we? I mean, that's an open question.
Like how many pixels are in a picture?
Cool. Yes. I can.
There is an answer in chat by Chris. Exposure. I think yeah, that's also a correct answer.
Yes, I think yes, that those are. I mean, there were many features actually, and in audio also, Rajat spoke about something called smell spectrograms or things like that. So yes, there can be multiple things that you can think of from workshop one. Like how features were introduced in workshop one also. So now we are done with feature extraction. So is that enough? I mean, because we know what are the features, we know how to feed them to the system, and we know what can be the outputs. But not, I mean, it's not always the same case everywhere, because not every feature is required, or and also often like doing like while we actually try to transform the raw data to the feature vector, we end up having redundant features as well. So it's important to select the best set of features that can actually help us to reach the best possible output or solution. So feature selection is the process that helps us to do that. I mean, as the name suggests, is basically helps us to select the best possible set of features. And obviously, since we are selecting a subset of features, it will reduce the processing time because the system needs to deal with lesser number of features now. So again, there are numerous strategies to do feature selection. There are things like recursive feature elimination and principal component analysis. I believe Dylan will be talking about principal component analysis later in this workshop as well. So yes, feature selection is very important too. So we are actually having right now we are having some kind of elementary idea of what are features, and we know what are the processing steps of features as well. But having said that, it's very important to remember that not every set of feature is suitable for every set of problem. So it's important to learn which set of feature will actually fit to reach the solution of which set of problems. So that's a really important skill to have, and that is why we need to learn what are the different features which can be used for different set of applications. So we are done with features. So we kind of right now have all the ingredients that we need to know before learning what before knowing what is machine learning. So let's quickly start our discussion on machine learning. So uh, basically computers are capable of learning the underlying pattern of data. So so moving to the first example that we talked about, that when we are given an image and if we are asked to differentiate between a cat and a dog, how do we actually do that? We actually from our like early days, like we know what are the different variants of cats and what are the different variants of images of dogs. So from that knowledge, we are able to distinguish between a cat and a dog from an image. So it's essential to teach the computer to differentiate between any such two classes. For example, in this case, we are taking the example of a cat and a dog. So, and also with the amount of data we have these days, we we need some sort of help to process this data. I'm pretty sure you people have an idea to the scale of data we have these days from our workshop one. So machine learning basically helps us out there. So again, we know machine learning can be able to solve many sort of problems, but should we actually use machine learning anywhere and everywhere? Like, suppose, let's take an example. So we are given a chart of 60 days, and we know the different tablet doses across the 60 days. So we have basically a lookup table, as you can see in the screen right now. So someone asks me, what is the tablet dose for day 2? Would, would, would you use machine learning for that? We already have the lookup table for here. Uh, so in the interest of time, I would say it's not required in this case to use machine learning, since we can already retrieve the answer from the lookup table. But given our data of 60 days, if we try to predict or have an estimate of the dose on the 61st day, we can definitely use machine learning in this case. And machine learning can really help us in these cases. So finding patterns and using them is what machine learning is all about. So essentially, it can solve any problem, but we shouldn't be using machine learning anywhere and everywhere. So we got we got an idea when to use machine learning. So let's start getting into details and terminologies of machine learning. So first comes labels. So when we were talking about the cat, differentiating between cat and the dog from an image, we know, I mean, we had to teach the machine to understand that this is a cat and this is a dog. So here the cats and dogs are the labels. So uh, like in real world examples also, like we always have two kinds of data sets. One is labeled and one is unlabeled. So labeled data sets are the ones where we kind of have the tags, like which particular data sample belongs to which class. And in unlabeled data, this is not the case. So quick recap with the leaf example, where we were supposed to differentiate between small leaf and big leaf plants. So what do you think are the data labels over here? You can speak up or type in chat.
Perfect. So Chris again in chat uh, says that it's potentially the species type.
Oh, good job. So we got the correct answer. So yes, here
Thanks, Chris.
the labels are, sorry. Oh, here the labels are basically small leaf and big leaf things. So it's important to know when we have label data and when we don't have label data. So now we know what are the labels. Again, the next thing which is extremely important is to know how much data we have. Do we have sufficient data, or do we don't have enough data? So this is just to visualize, like just to get an idea of what can we consider to be having sufficient data and what is somewhat less data. So as we can see in the curve, when the data set size is somewhat like around 1,000, the accuracy or the performance of the model is not that much. But as we increase the data side, we kind of see the accuracy increasing significantly. So that is when we can actually say that there is enough data. So again, the amount of data which is amount of data also varies from problem to problem. So uh, at times, even like 100 samples of data can be enough to reach solution. Again, for certain problems, even lakhs of data samples are not enough. So it's important to kind of have an idea when we are dealing with machine learning models, or what is the scale of data we should be expecting to have. So now we also have an idea about the data set size. So let's actually quickly jump to two basic set of machine learning problems. So when we have label data set, essentially we have a supervised learning problem. So right now we can teach the machine with the respective class labels of what is what category. In supervised machine learning problems, there are broadly two classes. One is regression and one is classification. So when it comes to regression, the label is basically quantitative one. So uh, a regression problem can be when we are trying to predict the stock market price of a company, when we are trying to predict the value of a house in California, something like that. And when the labels are categorical, it's a classification problem. So by categorical label, I mean when we are supposed to detect in between spam and non-spam, when we are supposed to differentiate between a big leaf or a small leaf, something like that. These are all classification problems. So let's quickly try to run a basic code example for regression. So let me see, yes. So in this problem, what we are trying to do is we are trying to predict or estimate the sales based on three types of advertising: TV advertising, radio advertising, and newspaper advertising. So these so X is our data set and Y is our predicted outcomes. So as it is very clear uh, from the problem formulation itself, here are Y is the labels and the features are TV, radio, and newspaper advertising values. So here what we did is we basically tried to fit a linear regression model to predict the sales value. And this particular value of 1.404 is nothing but the difference between the predicted value of sales and the actual value of sales. But this is a very basic regression model. There are other regression models as well, so which are non-linear. If somebody is interested, you are encouraged to go through the links that will be present in the collab. So we kind of have an idea of what is a regression problem. Next, moving on to a classification problem. So as I mentioned, like in case of classification problem, the labels will be categorical. So it's whether an email message is spam or not spam, something like that. So here, basically, we are trying to classify between apples and oranges, a very basic example based on some smoothness coefficient. So if the smoothness coefficient is somewhat like on the higher side, like 155 or 180, it's oranges. If it's on the lower side, like 135 or 110, this is it's according to the data set, it belongs to the apple class. So here we are using a very basic decision tree classifier, and once we are doing the classification training, we are trying to predict the class of the we are trying to predict if the smoothness coefficient is 120, what is the class, whether it's an orange or it's an apple. So in this case, the classifier predicts correctly it's an apple. So, but this is a very basic example where we have got only 4 samples. Again, just a reminder, like when we are really dealing with real world problems, the data sets are not that easy, and there are much more samples with much more number of samples available with us. So, okay, we are done with classification regression till now. And if anyone has any doubts, any queries, please feel free to speak up or type in chat. Okay, looks like we are going good. So moving on to the next part. So for any problem for any problem, it's important to know what sort of data distribution we are having. So if we are having a two-class problem, if the data can be differentiated or segregated linearly or not. So as in this case, in this image, we can see that these two classes can be differentiated by a straight line, but not all cases are that easy. So in the next case only, we can see here a particular straight line cannot actually differentiate in between the two classes. We can differentiate these two classes, but in this case, we have to take help of a circle or a circular arch. We will quickly introduce one of the very basic classifiers here as well. So we will talk about support vector machine, or very popularly known as SVM classifier as well. So what support vector machine does is basically tries to differentiate or segregate between two classes by choosing the hyperplane with the maximum merging. So I actually introduced many terms together. It's what is a margin, what is a hyperplane, and how does it work. So basically, if you go through the images, a hyperplane is nothing but a plane which is kind of separating two set of data set belonging to different class. So in the first case, for a two-dimensional space, a line is enough. So for a two-dimensional case, a hyperplane is nothing but a line. But for a three-dimensional space, it's basically a plane, because as you can see on the picture on the right side, a line cannot really segregate in between the red and green dots. So we know then what is a hyperplane. So can any hyperplane actually be used for segregating between two classes? As we can see in this picture, there are essentially three lines which can do the job, and each line actually correctly segregates between two set of data points. But we will essentially choose the particular line which has the maximum possible margin. And a margin is nothing but the distance from the nearest data point from each class with respect to the particular hyperplane. So we are basically choosing the line in the middle, which is actually having the maximum margin. So to sum up, the working principle is nothing but to look for hyperplanes which can classify the classes correctly, and then we can choose the one which basically maximizes the margin. So there are some links which you can refer to for knowing more in detail about some other sets of machine learning problems as well, where we do have multi-class or multi-label. So in multi-class, it's nothing but when we have more than two classes. And in case of multi-label, it's basically when you can associate every data sample with more than one label. So if we can, if in one image we can simultaneously associate it with multiple labels, then that problem essentially becomes a multi-label problem, multi-label classification problem. So these are some stuffs or some information about supervised learning. There are problems where when we do not have label data as well. That is basically the unsupervised learning part. I am not really going into detail, but if someone is interested, please feel free to refer to these materials and the codes. Uh, some of the, so right now we kind of have an idea of what is a supervised machine learning problem and what is an unsupervised machine learning problem. Now it's important to actually be aware of some of the tricks that we must remember while training using machine learning algorithms. It's important to understand what is a train test validation split, because we cannot really teach the computer everything based on the entire data set. We need to split the data set in 3 hubs. So basically the training data set is nothing but the number of data samples that we use to train the model. The validation dataset is the one that is used for tuning the parameters. So the validation dataset is something that the model will be seeing quite frequently, but those won't be used to train the model. And finally, when we report the performance of the model, we essentially report the performance on the model based on test dataset. So there are different optimal splits. Some people go with 70% with training, 15% for validation, 15% for test, but that varies from problem to problem. So we can like different set of such train validation test split actually works for different set of problems. Uh, Moving on, it's important to understand also what is overfitting and underfitting. These are the most common drawbacks that machine learning algorithms or machine learning models suffer from. Just to have a very basic idea of what is overfitting and what is underfitting. So overfitting is the case when your model is too trained. By too trained, I mean is what I mean is that your model is performing very well on the training data set, but it is not doing well with the test data set. And underfitting is the case when the model is not learning anything at all. So again, from the figure, we can see that underfitting is when the model is not learning to differentiate between them. And overfitting is when the model is overlearning or when the model is getting overtrained with the training data. So we have to go somewhere in the middle of underfitting and overfitting. Again, shuffling is very important while training the data sets. It's a very basic reason why we shuffle the cards after every round of a card game, so that we don't want to introduce any sort of bias or repetition. Then at points, we also come across data set where there is class imbalance. Like for example, in this case, we can see that one of the classes are having more samples, like approximately 90% of the samples belongs to class 1 and the other 5% to class 0. So in this case is also at times model performance is degraded. So it's important to deal with such data imbalance cases as well. There are different strategies which can help us out in these cases, like oversampling, undersampling, mixed strategies. So oversampling is nothing but sampling from the oversampling is nothing but sampling from the minority class, that is repeating the minority class values, and undersampling is just removing the removing the samples from the majority class. So we are done with the basics of machine learning, and we somewhat now know the answers of the first two questions that we first introduced today. So we know what is the problem, and we know how to we know whether or not machine learning can help us. Right now, let's try to figure out, if we have a solution to the problem, how do we know to what extent the solution is helpful, or to what extent the solution is actually solving the problem. So there are certain metrics to help us in such cases. There is classification accuracy, there is mean absolute error, there is mean squared error. Such metrics are there. Actually, the best way to visualize the performance of a machine learning model is to have a confusion matrix. So right now in the picture, you people basically are seeing the confusion matrix of of a binary classifier, where we are having the actual values along the rows and the predicted values along the columns. So it's important to understand what is a true positive value, what is a true negative value, what are false positive, false negatives. So you are encouraged to go through this part as well to understand better what are these values. For the time being, we can actually quickly walk through an example to understand what are different values from the confusion matrix. So suppose our problem is that we want to build a spam detector. We want to know which of the emails are spam and which of the emails are not spam. So here, just to have a better idea, the actual positive or the true positive cases are the cases where the emails are spam emails, and the true negative cases which are regular emails. So we are claiming that our system is, or our classifier is performing 90%, 99% accurate. And the data set we are having is like, we are having total 1000K emails. Out of those 1000K, we know that 999K are actually regular ones. So those are the true negatives. And those are the actual negatives. And we know 1000 of those 1000K emails are actually spam emails. So those are actual positives. And the classifier's performance data actually looks like this, where they are. So here, this is nothing but the true positive one. This is the true negative one. This is the false negative one, and this is the false positive one. So right now, what we will try to do is we will try to calculate the different measures that we have introduced so far. So let's quickly go and calculate let's quickly try to calculate what is accuracy. So as we mentioned, accuracy is nothing but the number of correct predictions by the total number of predictions. So in this case, accuracy is nothing but the summation of the green blocks by the total number of emails, that is 1000K. So I think the accuracy is coming to be somewhat like 99% if you are actually calculating it. Moving on to precision and recall. If we calculate the precision and recall in this case, those are coming as, the precision is 9% and the recall is 99%. So I am actually, in the interest of time, I'm just sharing the calculated values with you so that you can understand like how having 9% precision is basically leading us to have a recall value of 99%. So in this case, basically what recall what recall means is the number of actually correctly predicted spam emails uh, and sorry, the ratio of the correctly predicted spam emails and the actual number of spam emails. So the recall is nothing but 990 by 1000. And precision is nothing but the ratio of the actually predicted spam emails divided by divided by the actual spam emails and the wrongly predicted spam emails. So this is how we can basically calculate what is a precision, what is a recall. And the F1 score is nothing but the harmonic mean of the precision and recall. Now, why we are introducing so many metrics when we have accuracy itself? So the reason why we are doing this is there are in different cases, we need to prioritize on different matrix. So in cases where basically there is a large cost associated with the false negatives, we should be giving more priority to the recall. And opposite case happens when we should give priority to the precision. So this is just a rough idea of how to calculate the different matrix when we are given with a confusion matrix. There are also some other other matrix which can help us in understanding the performance of a machine learning model, like true positivity rate, true negativity rate, negative rate as well. So if you are really interested, we will be providing with the links of different resources which can help you out with such calculations. So I will stop here, and please feel free to ask if you have any questions, or at some point if you feel that you couldn't follow.
So yeah, just to kind of reiterate on what Ramita was saying too, is I realized that, this is a lot of material, especially if you guys haven't, seen some of this stuff before. So what I would encourage you to do is we'll be providing this notebook. So go ahead and, look through it and try and familiarize yourself with it, as much as possible. And then there's also some links that we provided in there as well if you want some more details too. Oh. Sorry, I just realized I was completely muted that whole time, wasn't I?
I think
No, we did.
yes.
Okay, for some reason it just it popped up as I was muted. Anyway, yeah, so as I was saying, yeah, just go ahead and, if you're curious, follow those links and explore some of that material.
I think Dylan will have a 10-minute break now, 10 minutes or 5 minutes. And guys, feel free to post any questions in chat, or you're always like, feel free to speak up as well. So after like this break, Dylan will take over and we will go through some of the examples in detail. And also like we will be, as Dylan was mentioning, we will be sharing this collab notebook with you with the links. So I will stop sharing.
All right, so I think we'll probably get started again. Awesome. So as Ramita mentioned, what I'm going to do is just walk you through some simple examples that will hopefully kind of reinforce some of the ideas that we introduced, as well as provide you with some examples of using Python. All right, can you all see my screen?
Yes.
Perfect. All right, so I'll try and keep this pretty high level. So, you know, if you've never used Python before, hopefully you can kind of follow along, but, you know, feel free if you do get lost to interrupt me and ask any questions, as well as if you do want me to provide some more details, I'd be more than happy to do that as well. So the first thing I'm going to do in this notebook is I'm just going to import some useful libraries. So the first one that's going to be really useful for us is this scikit-learn library, which what it does is it will provide some pre-written algorithms that are going to be incredibly useful, as well as some functions that will allow us to easily evaluate the performance of these algorithms. And then for this specific example, I'm just going to load in a data set that they've, you know, they already have in scikit-learn that we can play around with. And so while I do that, I just want to ask, based on what we've covered, you know, what are some of the very first questions that you guys, you know, would like to ask? Like, let's say, you know, I present you just with a data set. What are some of the first questions that come to your mind that you want to know about this data set?
Like what is the data set measuring, and then what are the associated features of the like main object or thing that it's measuring?
Exactly. Yeah, that is a great point. So I'll just go ahead. I'll kind of show you what's contained in this data set. So don't necessarily worry about the specifics here, but it's contained in a Python dictionary. So it's, you know, it's got these keys and values. And so it gives us, for instance, one of the keys is going to be data. And if I go ahead and look at that, what we can go ahead and see is that, you know, it's just that it's some raw data points. And then there was another key that's called target, which gives us this. So based on kind of what we talked about, you know, classification versus regression, can we kind of, you know, take a guess at, say, what problem this one would be? Anybody got a guess?
Komal says it's a classification problem.
Exactly. Yeah. So as you can kind of see, we have, you know, they may be numbers, but it breaks down to just these three different labels that we can see. So we have, you know, the three different classes. And then we can go ahead and look at, I think it provides, yep, it provides target names. So we had the three classes that are 0, 1, and 2. And then we have target names, and we can see what we're actually predicting. So for this simple example, what it actually is we're predicting the species of a given flower from some specific features that we have. So if I go ahead and I look and I return to the features, which I've done here. I can kind of look at the other thing that I want to kind of ask about is like, what is the, you know, like feature dimensionality? How many samples do I have of the feature set? So what I can go ahead and do that is, if you remember, I have the data just indexed here. Using a different method from a NumPy array. Don't worry about the specifics if you're not that familiar, but we can actually get the shape of that data. So we can see, in the first column that we have 150 samples, and then there's 4 columns. So we have 4 features. So that's just kind of what I want to really get you guys to commit to memory is whenever you're faced with, any task, what we really want to do is understand the data that we have. So again, we have 150 samples, we have 4 features, that's our feature dimension, and then we're trying to predict 3 classes. And so another thing that Ramita had mentioned was that, potentially we could be dealing with like imbalanced classes in a classification problem. So that's another thing that I could potentially want to check. And I can do that with just a built-in function here. Did I import this? I think so. I might need to do that just a sec. So I can just import a function called counter. And then I can just count the labels that I have. And we can see that for each of the 3 labels, we have exactly 50 samples. So we have a perfectly balanced data set. All right, so again, just to provide another way of kind of getting a feel for the data as well, what I can do is, depending on the size of the feature space, it's hard to visualize or think about like how these data points exist in that feature space. But one of the thing I can do is I can use PCA to reduce the feature dimension to a dimensionality that we can visualize. So I'll go ahead and do that here. I'll reduce the number of features down to 2, and we can go ahead and plot this. So when we go ahead and do that, we can actually see that there's some pretty clear boundaries between the 3 classes here, specifically when we're like looking at classifying this red class from the blue and green classes. We have quite a bit of margin when we're looking at the x-axis there. There's quite a bit of separation. So you can imagine we could pretty easily draw a line here that acts as a boundary for separating these, and we say that will be classified as this red class, and so on. So just want to note that this is kind of a toy example. It's this data is pretty nice that it separates that well, and that we can even visualize this in 2 dimensions. As we get to higher feature dimensions, and as we get to more complicated problems, this separation might not be as readily apparent, but that's where the computer really comes in and machine learning really comes in, and being able to figure out patterns and to be able to draw these boundaries when they're not so obvious. All right, so now that we kind of have an understanding of our features, we have an understanding of the problem, we're dealing with a classification problem, all that, we can start thinking about what models can be used for this problem. And kind of the way I'd like you to think about this is quite simply, it breaks down to like an input and then a model and then an output idea, right? So those 3 stages. So we have, we already have our features defined. We already have labels. Those are going to be our inputs. And then our outputs is after, we trained a model, we can evaluate the performance and everything. But now I want to choose, a model that will help us solve this task. So that's where scikit-learn, as I mentioned, comes in really handy because it's got all these different, algorithms and models, pre-built for us to use. So what I'm going to just go ahead and do is run a really simple model to kind of see what performance that we can get. So I'm just going to be running a KNN here, and we can see, I just define the model here. And then all it is I'll just fit it on the training set. Actually, that is one thing I don't think I covered, sorry. Yeah, to step back a little bit. So previously I had, the data set with 150 samples. And one of the things that we want to do in, machine learning is we have to be able to train the model. And then we also have to be able to evaluate the performance of the model, right? Because if, we trained a model on all the available data, in theory, what we could actually do is just have a lookup table for each data point. We know the label, and we just say when you get that data point, it's classified as that label, and you can just get 100% accuracy or 100% of whatever metric that you're looking at that way. What we really want is a model that we can train on some of the data, and then when we test it on different data, data it's never seen before, then that model still performs well, and it still classifies correctly. So in order to do that for this example, what I'm going to go ahead and do is split up the data set into a training set and a testing set. So I'll do that here. So again, this is another nice function in scikit-learn is this train test split. And this is actually another cool thing with using the Google Colab notebooks is that you can easily see, the arguments for functions. If you've never used this, the specific function before, we can go ahead and kind of see what it does. So it will give you, if you just hover over it, it'll give you a quick description. It'll tell you the different parameters. So for instance, there's one parameter here called test size, which will determine the amount of data that I want to split off and make as the test set. So for instance, if I just go here and I say test size is equal to 0.3, then it will go ahead and split off 30% of the data for the test set. And we can see that here. So now, 45 samples belong to the test set, and now 105 samples belong to the train set. Or I can change it to say, 25% of the data, and it will split off 25% of the data. So you'll commonly see, again, all this kind of varies on the problem and the amount of data that you have, but you'll see common values like a 70-30 train test split or a 75-25 or an 80-20. Again, it depends on the problem. It depends on how much data is available. So now that I have that split off, I can return back to my model here, and I have this train data set. And I have this separate test data set. So this function, all it will do is, it'll fit that model on the training data. It'll, for lack of a better word, just train that model. And then we can go ahead and see how it does on that holdout test set. So just running this code, we can see what the train model predicts for this test set. And then we can go ahead and compare the predicted classes against the actual classes to get a sense of how the model is performing. So, as you can see, as I kind of showed above, that, this actual classification problem is not that difficult as far as things go. So we can kind of see that. I just tried, the first model I tried, this simple model, we're able to get almost a 95% test accuracy, which I think I had like 38 test samples. So it's basically we're getting like 36 out of 38 correct. So this is kind of what I would encourage you to do as you're initially exploring a problem too, is after you've kind of understood your data set, go ahead and run some simple models on it, kind of get a sense of, what is a baseline of performance for this particular problem. So in this case, we can see, again, that, it's pretty easy to do. We can get really, really high performance. And I can go ahead, I can change some of the inputs, some of the hyperparameters of this model, and we can see if we can get different performance. In that case, still the same, but I can also actually go ahead and, change out the model that I'm trying, as simple as this. So, we still have our input, and I'm just changing the model that we're, that we're trying to train, and I can evaluate in the exact same way. So now I've changed to a support vector machine, and we can see that I haven't even, really played with the parameters or anything for it, but we can achieve, even slightly higher accuracy with the default parameters for it. Are there any kind of questions about any of this material so far? Cool. So yeah, again, just to reiterate, this code will also be available for you guys to kind of reference and to kind of play around with. And yeah, these ideas are, pretty universal. The problem can get harder. The amount of classes can increase, the amount of features, amount of samples and everything. But at the end of the day, we just have, some input data set. We have some model that we're going to train on, and then we have to have some way to evaluate the performance of that model. Cool. So touching on another thing that Ramita just briefly mentioned was validation. So as I mentioned up here, there's, certain hyperparameters for these models that we can set, right? And we want to have a sense for, what are the best parameters? What are the best combination of parameters to give us the best, generalized performance? But what we want to do is we want to keep that test set to the very end of this process, right? We want to go through this process. We want to come up with the best model, and then at the very end, we want to go to this, this test data set that we haven't touched before. The model hasn't seen in any way before, and test it and give kind of this final performance and really certify that this model learns something that generalizes to data that it hasn't seen before. So if we want to go about kind of, tuning hyperparameters for these models, we can do cross-validation. And then in this case, these models are simple. Training is quick, so we can do this cross-validation versus just having a completely split out validation set. I'll provide some more references to when you should think about using like cross-validation versus when you have enough data that you don't need to do this cross-validation thing. But the general idea is we're just trying to get a sense for what parameters give us the best performance. So what I'll go ahead and do is I'll sweep across different values of K here. So again, K is just the number of neighbors that the KNN looks to when it's trying to make its prediction. So if we view this here really quickly, a training data set, existing, if I give you a new point, and what a KNN does is it'll just kind of look around at the nearest data points and, basically take like a majority vote of those data points. So in this case, we're surrounded, by green data points. So it'll label this hypothetical point as the green color. And we can see the result here. So initially when we start at 1, we're getting, pretty good performance. We can increase it a little bit and we're seeing, kind of the maximum performance. And then as we keep on increasing this parameter K, then we get some, performance degradation. All right, and then this is just, again, illustrating the fact that we can just give it, a new data point that it hasn't seen before. So the model's, been trained and we're giving it this new data point that it hasn't seen before. And it will go ahead and predict what the class of that data point is. So in this case, we give it and it says it's, a Setosa. Cool. So that's kind of the, the very basic, very high level to machine learning concepts or even any of the code that I've given here. Cool. So and you're trying to code something up. Even simple examples like this, as a reference, are your friend. So yeah, just it's one of those things where the more code you see and the more code you kind of copy and just try typing out yourself, the more familiar you get with it. All right, and then just really quickly, do we have a question? All right, so I just want to kind of illustrate that, these ideas carry through to even more complicated examples. So I'm going to go ahead and load in another data set and we'll kind of, ask the same questions about it that we asked previously, right? So in this case, the data set is the fashion imness data set, which I've printed out some information about it, I believe here. Yep. So data set have a lower it's a 10 class data set. It's just some low resolution grayscale images of various clothing items, where there's 10 different clothing items. Cool, so I've gone ahead and just split this up into again, some of the questions that we can ask about it. We've already asked about the number of samples. The other thing is, what's our feature dimension here? What are our features? What do they represent? In the previous example, the 4 features we were given are, some actual looking at pixel values. And for a simple example, what I can do is these images are 28 by 28, but I can go ahead and just flatten these images so that we get a 700 that 60,000 samples by this 784 pixel values. And that the kind of questions that we're asking are, you know, the algorithm to do in this case to be able to recognize, you know, from pixels, what certain objects are. In this case, you know, clothing item, and it's neural networks could potentially help us out, you know, quite a bit with. So what I'll do here is I'm just using TensorFlow, which is another really useful library to define a simple neural net. But again, it's you know, if this is the first time that you've seen it, there's kind of a lot of details that you know, you kind of get lost in. But I've provided some you know, quick references in the the collab notebook that we're going to, the specifics of that's a great reference. But the general idea is, you know, this model is definitely, you know, more complicated than, you know, the KNN that we're training previously. But, you know, the ideas are the same, right? We still have, you know, input data that we're dealing with, and we still have, you know, this model that we've defined, you know, complicated, not complicated, whatever it is. We just want to fit that model to our training data, which I've done. And after we've done that, we want to evaluate the performance of the model. So just some, oops. Cool. So yeah, some really, you know, probably, you know, the simplest neural net you can think of, but it'll just take some time to train. It's training on the trained data set now. And then we can go ahead and evaluate the performance on the test set. So we can see that, you know, this is a simple model. I didn't even train it for very long, but we actually end up with some pretty high performance on this holdout test set. So we got 87% accuracy here, which if you remember, we have a 10 class data set that's, you know, perfectly balanced. So, you know, accuracy is still a good metric for us to evaluate. And this is a, you know, a high value that we're getting. Are there any quick questions about any of that? All right. So yeah, just some more little specifics about what we're looking at with the neural network. So in this case, when we're looking at the outputs for it, what it will give us are output probabilities. So, and again, if you haven't seen this before, you know, don't necessarily worry about the specific details, but for the output layer of the neural network, you know, there's 10 output nodes for the 10 classes. And the output values are going to be the probabilities of what it thinks, you know, how likely it thinks that the input image belongs to that specific class. So, you know, as we're looking along here, we can see that, you know, it's got a very low probability, like almost zero, for the vast majority of these you know, these potential classes, except for, in this case, for this first example, this for the 10th class, it's saying it's pretty confident that, you know, that image is that class. And so I'll just go ahead. We can actually see the print out the input image, and we can kind of see like it, you know, it looks like a shoe or a boot or something. So I'll go ahead and I'll look at oops, the fashion imnist labels. And I think it should give us what those 10 classes are. So if I go down here, yep. So this final class here is what it calls an ankle boot. So that, you know, that's what we're getting here. Is this input was indeed like, you know, something that looks like a boot. So this classifier is getting that correct. And we can also look at you know, just the second example. So can anybody tell me like which class it's most confident about here?
The third one.
Exactly. So if we go ahead and we look, the third one, it's calling a pullover, which I think should just be like a sweatshirt, right? So we can go ahead and also look at that image. And yep, that's it, exactly what we're getting. Cool. Any questions about that? Awesome. So again, that's just a you know, a really simple example. Hopefully, you know, if you want to take the time to just play around with this, maybe get some familiarity with some of the code, you know, that would be great. It's there for you to kind of experiment with. And then also in the main notebook here, as I mentioned, we'll just have you know, just some more details of some of what we've talked about. So for instance, if you want to you know, learn some more specific details about exactly what the components of a neural network are. Let's see, where is it? I've provided them here. Yep, here we go. So yeah, just some definitions, some things to get you started. And yeah, if you know, if you're curious about that, yeah, feel free to check it out. All right. So I think that's everything I had for you know, just running through some basic examples in Python and some of the basic principles of ties back to the very beginning of the workshop. You know, we have these three things that we want to take away from all of this. We want to be able to, you know, understand the problem. In this case, you know, what is the kind of task that's laid out in front of us? Are we looking at, you know, classification, regression, something of that nature? And then, you know, how many samples do we have? You know, what features do we have? Are features relevant? You know, what's the dimensionality of the features question? Is we can ask, you know, is machine learning, you know, can it help us out with this problem? Or even more specifically, like what algorithms could be useful for this problem? Again, just to really reiterate, because I know it's such a hot thing nowadays, deep learning, but it's not the best solution for all problems. It's not the best solution for most problems, I would say. Deep learning is really useful when, you know, you have a lot of data and you have really complicated relationships that you need to learn. So kind of my advice is always to start out as simple as you possibly can. Start out with some of the simpler algorithms and SK learning, kind of get a feel for, what performance that you can achieve. And, if you do have a larger data set, or you feel like you can squeeze more performance out of it, then neural networks, deep learning can definitely be an option for you. And then finally, we want to be able to, evaluate how well we've done on a specific problem. So in this case, we want to be able to ask and answer, how well did this algorithm learn? How well are we performing on this data set? What's the best metrics to measure performance here? Because if we have, if we're in classification and we have an imbalanced data set, accuracy could give us, some misleading ideas for how well our algorithms performing, things of that nature. So we really want to be able to, again, just to reiterate, really understand the problem, understand what models can be beneficial, and then understand how well the models are performing. All right, any questions or follow-up for that? All right, someone's got to have one question, one nagging question.
So the question is, how do we get the original labeled data sets? Do people label them by hand?
Yeah, so that's something that we've kind of been glossing over a little bit is, data labeling is a big task. If you're trying to, formulate a problem, build a data set for yourself, then that labeling component is going to be, hugely time consuming. Yes, you'll most likely have to have human annotators, go through and annotate for specific classes or what have you. So that's a really time-consuming step. It's really important. But yeah, that is one thing to keep in mind. So what we'll want to do right now is essentially, provide you with data sets where that's already been. The labels are already collected and established and everything, just to kind of cut down on the overall process of building and evaluating the data set. But yeah, that's a great question.
I believe,
Sorry.
no, I was just telling that all of you will be coming across different set of problems when you will be doing the projects. But this is just like a high level overview of how machine learning can help you out in solving those problems. As Dylan mentioned, this collab will be available to you like in a week or so. So we encourage you to go through them and like go through the codes and try to understand. And hopefully this almost on time. I will hand it over to Kathy if like we do have any last announcements, and also like you were mentioning something. Sorry.
Oh, just a fun fact, since Dylan was mentioning regarding data sets. So you might have heard about ImageNet because it's been in news. Like everybody keeps talking about ImageNet being a very large human database, like image database. So the
Nicola, you might want to explain what ImageNet is.
yeah, so ImageNet is like a big image data set which like powers all this deep learning algorithms which we use often to like recognize different like places and all other stuffs around us. So just a fun fact I just came across, that the ImageNet was hand labeled, or like there was a human baseline. This was one graduate student who did it. Yeah, so just I wanted to mention like a fun fact. So yeah, hand labeling is a part of the process. So, and that's like based on certain instructions and everything. So it's usually like fun part. Yeah.
Sorry guys, my internet is just having a lot of problems today. So I will not slow you guys down by saying much, but I'm just hoping the recording today will work well, because we do have a lot of very good information, and we have some people due to midterm conflict couldn't attend it. So hopefully this will be very helpful to them.
Thanks, Kathy. I know you guys are all busy with like your midterms, but we'll send out some more information in the coming week. We just want to make sure you got a chance to like run the collab for workshop 1, get your hands like a little bit like, dirty, like running some code yourself, and you guys can use the code that Remita and Dylan are also going to share. But maybe we'll send that like next week in honor of like the midterms. Unless you think, I mean, all these resources are already shared with you. The wiki has been shared with you, so it has everything you need to know. So if somebody is like done with midterms and want to look at some of those things, you can already do that. You don't need to wait for us. But we'll also be sending like a reminder next week. And hopefully all of you are like reaching out to your mentors and like pestering them about your homework, about your projects. Yeah, but do let us know if you're too busy and you can't show up for these workshops, or if you can't work on the project, just drop Kathy or drop one of us like a note on Slack. Would really appreciate that. Thanks, Kathy.
No problem. Okay. All right. If we don't, there's much